Welcome to our latest video on the topic of carboxylic acids, physical properties and acidity. This video is suitable for A-level students. By the end of this video lesson, you should be able to describe the intermolecular forces present in carboxylic acids and be able to explain how these are linked to physical properties such as boiling points. You should understand why carboxylic acids are classed as weak acids and how their acidity is affected by increasing the hydrocarbon chain length in the molecule. And you should be able to explain the order of relative acidity of carboxylic acids compared to phenols, alcohols and water, and how this can be demonstrated. Now, in our previous video on carboxylic acids, we learned that the functional group of this homologous series is a COOH group, and ethanoic acid is an example of a compound that belongs to this homologous series, and ethanoic acid has a CH3 attached to a C double bond O and an OH, and many carboxylic acids occur naturally, the simplest being methanoic acid, which is produced by ants, and other examples of carboxylic acids are lactic acid, which is a more complex carboxylic acid formed when milk ferments. Lactic acid is also produced when muscles exercise, and other examples of carboxylic acids include citric acid, which is found in lemons, and malic acid, which is found in apples. Now, in this first section of the video, we're going to look at the physical properties of carboxylic acids. And when talking about physical properties, we're really talking about melting points, boiling points, and their solubility. Now, carboxylic acids have relatively high melting points and boiling points compared to their parent alkanes. And this is due to their ability to form hydrogen bonds with other carboxylic acid molecules. Now, hydrogen bonding is the strongest intermolecular force, and it occurs when you have HOs, HNs, and HFs. Now, when hydrogen is bonded to fluorines, nitrogens, or oxygens, we have the biggest electronegativity difference, and that's why hydrogen bonding is the strongest intermolecular force. Now, carboxylic acids have the strongest hydrogen bonds of the molecules that we study, and carboxylic acids will exist as dimers, pairs of molecules bonded together. For example, pure ethanoic acid is a liquid at room temperature. It has a high melting point of 16.7 due to the dimers it contains. Now, 16.7 might not seem like a high melting point, but if you compare it to the melting point of ethane, the alkane with two carbons, that has a melting point of minus 182.8 degrees C, it does have a high melting point. And this is because of the strong hydrogen bonds it contains and the fact it exists as dimers. Now, if the temperature of ethanoic acid drops below 16.7, the ethanoic acid freezes and becomes a solid. Due to this tendency, pure ethanoic acid is known as glacial ethanoic acid. Now, the melting point and boiling points of carboxylic acids are much higher than alcohols, haloalkanes, aldehydes, and ketones. And the following diagram shows two molecules of ethanoic acid hydrogen bonding to each other and existing as dimers. Now, when drawing a diagram to represent the hydrogen bonding that exists between two molecules of ethanoic acid, it's important that you put in the dipole that exists on the OH of the carboxylic acid. So the oxygen is delta minus and the hydrogen is delta plus, and that's because oxygen is a lot more electronegative than hydrogen. And a delta minus oxygen on one molecule can bond to a delta plus hydrogen on another, and this is a hydrogen bond. Now, you'll notice on this diagram I've also put in the lone pairs of electrons that exist on the oxygen, and the oxygen has two lone pairs, and one of these lone pairs of electrons contributes to the hydrogen bond. So the oxygen is able to form a hydrogen bond with each lone pair that it has. Now, it's important to mention that the hydrogen bonding that exists between molecules of carboxylic acids will be stronger than the hydrogen bonding in alcohols and amines, and therefore carboxylic acids will have higher melting points and boiling points than both alcohols and amines. Now, the other physical property that we have to consider is solubility. And the first few carboxylic acids in the homologous series have high solubility in water. However, the solubility decreases as the hydrocarbon chains get longer. Now, to explain why ethanoic acid dissolves in water, I'm going to draw a diagram. And on my diagram, I'm going to put in the dipoles that exist in ethanoic acid. And the main dipole that I'm interested in is between the O and the H in ethanoic acid, because the oxygen's a lot more electronegative, and therefore there's a strong dipole between the O and the H. So oxygen's delta minus and the hydrogen's delta plus. Now, the reason ethanoic acid dissolves in water is that this OH group can form hydrogen bonds to water. So the oxygen in a carboxylic acid is delta minus and can form a hydrogen bond to the delta plus hydrogen in water. And the hydrogen in the OH group in carboxylic acids is delta plus, and this can form a hydrogen bond to the delta minus oxygen in water. Now, when drawing a hydrogen bond, it's also important that I put in the lone pairs on the oxygen, and there's two lone pairs, and one of these lone pairs can contribute to the hydrogen bond. So you'll notice that in water there's two lone pairs, and one of these lone pairs on the oxygen is forming a hydrogen bond to the delta plus hydrogen in ethanoic acid, and the other lone pair is forming another hydrogen bond to another delta plus hydrogen in ethanoic acid. So the reason I'm showing you this is I want you to understand that when water forms hydrogen bonds to the OH group in carboxylic acids, it gets in between carboxylic acid molecules, and that's why carboxylic acids are able to dissolve. Now, if you increase the length of the hydrocarbon chain, you're increasing the part of the molecule that is non-polar, which is hydrophobic. Alkyl chains do not have dipoles, they are non-polar, and they hate water, and they disrupt water's ability to form hydrogen bonds to the polar OH group in a carboxylic acid. So whether a substance dissolves or not depends on how big is that polar part in the molecule compared to the rest of the molecule, which dislikes water, which is hydrophobic. And as you increase the length of the hydrocarbon chain, you're increasing the non-polar part, and therefore you are disrupting water's ability to form hydrogen bonds to the carboxylic acids OH group. So now let's test your understanding of physical properties with some practice questions. So this first practice question comes in 3 parts. Here's the first part. Pause the video, have a go at it, and then we're going to look at the next 2 parts of this question. So here's the next 2 parts of this question. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. Now, question 1A is asking you to suggest a boiling temperature for butanoic acid. Now, ethanoic acid has a boiling temperature of 118 degrees C. And when you add a CH2 group to form propanoic acid, this boiling temperature rises by 23 degrees C to 141. Now, you get a similar trend if you go to hexanoic acid, because this has a boiling temperature of 205. So hexanoic acid has 3 additional CH2 groups compared to propanoic acid, and there's a 64 degrees C difference. So roughly there's a 21 degrees C difference for every CH2 group. So if you add 21 degrees C to propanoic acid's boiling temperature, you will get 162, and the examiner accepted 165 plus or minus 5 degrees C. So now let's go for the next 2 parts of this question. So part 2 is asking you to describe the trend in boiling temperatures as the number of carbon atoms in the acid increases, and to suggest a reason for this effect. So if you said that as the number of carbons in the acid increases, the boiling temperature increases, you get 1 mark. And this is due to the increase in van der Waals forces that exist between the molecules, because the longer the hydrocarbon chains, the more electrons there are and the more temporary dipole forces there are, or van der Waals there are. So to get the 3 marks, you get 1 mark if you said that as you increase the number of carbons in the chain, the boiling temperature increase. You get the 2nd mark if you said this is due to the increase in van der Waals forces. And the 3rd mark is if you said that the van der Waals forces are between molecules. So that gets you 3 marks in total. So for part 3, you're asked to explain why the carboxylic acids become less soluble in water as the sizes of the molecules increase. Well, as the size of the molecule increases, you're increasing the non-polar part of the molecule, the hydrocarbon chain. And this is disrupting the OH group's ability on the acid to form hydrogen bonds to water. Now, another way of looking at this is if you increase the alkyl chain, the polar OH group is a smaller proportion of the molecule in total, and therefore it's having less of an impact in the solubility. So to get the marks, there's 1 mark if you said that if you increase the size of the molecule, you're increasing the non-polar part of the molecule, 1 mark for that. And then if you said it's disrupting the OH group's ability on the acid to form hydrogen bonds to water, you get the 2nd mark. Now in the next section of this video, we're going to look at the acidity of carboxylic acids. Now carboxylic acids, such as ethanoic acid, are weak acids. And weak acids are substances that partially split up into H+ ions when you put them in water. Now remember, a strong acid totally splits up into H+ ions when you put them in water. And I've shown here an equation to show the ethanoic acid molecules breaking up into ethanoate ions and H+ ions. And you'll notice that an equilibrium is set up, the reaction is reversible, and typically in every 1,000 molecules of ethanoic acid, around 4 stay split up at any one time. So the equilibrium is very much on the left hand side here. Now you should remember from year 12 chemistry that the pH of a solution is a measure of the concentration of H+ ions, and the lower the pH, the more H+ ions are in solution. And if you think about ethanoic acid splitting up compared to hydrochloric acid splitting up, if I had 1,000 molecules of hydrochloric acid, I would have 1,000 H+s because they would all split up. And typically, for every 1,000 molecules of ethanoic acid, there's only about 4 split up at any one time. So you can see that there's a lot more H+ ions produced from a strong acid than a weak acid. Now the acidity of a carboxylic acid depends on the stability of the negative ion formed when the carboxylic acid splits up. So it depends on the stability of the carboxylate ion. Now the less stable this anion is, the more likely H+ ions are to attack it and recombine with it and reform the original acid. So in other words, to push the equilibrium to the left hand side. Now if this anion is less stable, there's less H+ ions in solution and the acid is weaker. Now carboxylic acids have a way of stabilizing their anions, and they do this by delocalizing or spreading out their electrons between the COO in the carboxylate ion. And you can see in this diagram I've shaded in green the negative charge spreading out over this region. Now this is quite effective at stabilizing this anion, and it is more stable than a phenoxide ion, which we covered earlier in the course when we studied phenol's acidity. You remember that phenol is acidic because its phenoxide ion can stabilize by the negative charge spreading over the benzene ring. Now this is more effective than that. Now you might be thinking, what causes these electrons to delocalize over the COO region? Well, it's because of the electronegativity of the oxygen atoms, and therefore the electrons will spend more time located around the oxygens than the carbon because of this electronegativity. So more spreading out or delocalization of the negative charge takes place in a carboxylate ion when the negative charge spreads over the COO region than takes place when the negative charge spreads over the benzene ring in a phenoxide ion. And therefore, these ions produced by carboxylic acids are more stable than phenoxide ions, and therefore, if they're more stable, they're less likely to be attacked by H pluses, so there's more H pluses in solution, and carboxylic acids are more acidic than phenol. Now, if we have 1,000 phenol molecules, around about 1 in every 1,000 will have split up into H plus ions. And this is compared to about 4 in every 1,000 for ethanoic acid. Now, ethanoic acid is around about pH 3, where phenol is around about pH 5.5. So you can see that phenol is a weaker acid than ethanoic acid. Now, the acidity of carboxylic acids depend on the stability of this carboxylate ion, and the more stable this ion, the less likely the H plus ions will attack it and recombine with it, and the more acidic the acid. Now, carboxylic acids are relatively acidic because they can form this stable anion, and the negative charge can spread over the 2 oxygens and the carbon, making it more stable and less likely to recombine with the H+. Now, if you increase the hydrocarbon chain in a carboxylic acid, you are increasing the size of the alkyl group. Now, alkyl groups push electrons and negative charge towards things, so they counteract this ability to stabilize the anion because they push negative charge towards this oxygen, which I've highlighted here. And this makes the anion less stable. And the less stable the anion, the less H plus in solution, and the less acidic the carboxylic acids. So the most acidic carboxylic acid is methanoic acid. And if you increase the hydrocarbon chain, you're making the anions less stable because the alkyl group is pushing electrons towards the O, and therefore you're making the anion less stable, more likely to be attacked by H+, and you're making less H+ in solution, and you're making the acid less acidic. So increase the hydrocarbon chain length, you make the carboxylic acid less acidic. Now in the exam you will be asked to compare the acidity of carboxylic acids with molecules such as phenol, ethanol and water. Now phenol is acidic because phenol splits up into H+ ions and phenoxide ions when you put it in water. And like ethanoic acid, it's a weak acid because it partially splits up into H+ ions. Now the reason phenol is more acidic than water is because the phenoxide ion is more stable than the hydroxide ion. Now the reason the phenoxide ion is more stable than the hydroxide ion is that the negative charge can spread over the benzene ring, making the ion more stable, less likely for the H+ to attack it, so there's more H+ ions in solution, so therefore it's more acidic than water. Now in the hydroxide ion, there is nothing to take the electrons away from the O, so therefore this ion is less stable than the phenoxide ion, there's less H+ in solution, and is less acidic. Now, ethanoic acid is more acidic than phenol because its ion, the ethanoate ion, is more stable than the phenoxide ion, because the ethanoate ion can spread out the negative charge more than the phenoxide ion. And it does this, as we've seen, by delocalizing the negative charge over the COO in the ethanoate ion. So after discussing the acidity of carboxylic acids and how this compares to phenol, we're now going to look at the acidity of alcohols and see how this compares to water, phenol and carboxylic acids. Now alcohols are less acidic than water, and I've drawn the equilibrium here of water splitting up into hydroxide ion and hydrogen ions, and I've drawn ethanol splitting up into ethoxide ions and hydrogen ions. And the reason that ethanol is less acidic than water is once again to do with the anions. An ethoxide ion is less stable than a hydroxide ion. And this is because the alkyl group in the ethoxide ion pushes electrons onto the oxygen, and that makes the ion less stable. Now, if the ion is less stable, it's more likely that the H plus ions will attack it and recombine with it, and therefore push the equilibrium to the left. So the ethox ion is less stable than the hydroxide ion, because in the ethoxide ion the charge is on the oxygen because the alkyl group is pushing electrons onto the oxygen, and therefore if the ion is less stable, there are less H plus ions in solution because the H plus ions are more likely to attack it, and therefore if there's less H plus ions in solution, it's less acidic. So to summarize, ethanoic acid is more acidic than phenol, which is more acidic than water, which is more acidic than ethanol. And the reason that ethanoic acid is more acidic than phenol, water and ethanol is because it has the most stable ion. And it's the most stable ion because the negative charge can spread out over the COO and it spreads out very efficiently. Phenol is the next acidic because the phenoxide ion is the next most stable ion because the negative charge can spread over the ring. And ethanol is the least acidic because the ethoxide ion is the least stable ion, and therefore it's more likely to be attacked, and therefore there's less H plus in solution. So we've seen that both ethanoic acid and phenol are weak acids. However, there are big differences between them. Ethanoic acid is a stronger weak acid than phenol, and this can be seen by measuring the pH and observing the reactions. Ethanoic acid has a pH of around 3 compared to phenol, which has a pH of around 5.5. And ethanoic acid reacts with alkalis such as sodium hydroxide and with metal carbonate such as sodium carbonate and sodium hydrogen carbonate to form a salt, carbon dioxide and water. And therefore the carbon dioxide would cause lots of fizzing, and the reaction with the metal carbonate can be used to test for a carboxylic acid. Now in contrast, phenol is a very weak acid that reacts with sodium hydroxide, but it's not acidic enough to react with sodium carbonate or sodium hydrogen carbonate. So if you add a metal carbonate to phenol, you will find that it doesn't fizz. So that's an important difference between carboxylic acids and phenol. So now let's test your understanding of acidity with some practice questions. So here's the first practice question we'd like to have a go at. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So this first question is asking you to complete the following table with any observations. And there's 3 compounds. One's got a phenol group, one's got an alcohol group, and one's got a carboxylic acid group. And you have to fill in the table for the compound with the phenol group and the compound with the carboxylic acid group. Now the first compound, propofol, has a phenol group, and it's asking you what would happen with universal indicator paper Well, as I mentioned previously, it's around about pH 5 to 6, so therefore it would go yellow or orange with universal indicator paper. You then have to complete what would happen if you added sodium hydrogen carbonate solution to propofol. Now, because it's got a phenol group, phenol does not react with metal carbonates or metal hydrogen carbonates, so there would be no reaction. Now, for compound M, you're asked the same question. What would happen with universally indicated paper and what would happen with sodium hydrogen carbonate solution? Well, compound M contains a carboxylic acid group, so it's going to be a stronger weak acid. So they accepted orange or red with universally indicated paper, and carboxylic acids react with metal carbonates and metal hydrogen carbonates. So if you add sodium hydrogen carbonate solution, you would see fizzing because carbon dioxide would be produced. So now have a go at questions 2 and 3. Read through the questions, pause the video, have a go at them, and then we'll go for the answers. Now question 2 is asking you to explain why phenol is more acidic than alcohols, but less acidic than carboxylic acids. And there's 4 marks for this question. Now, I recommend that you draw out the different equilibrium that exist, showing the ions, and then it's easier because you can say which ion is more stable and which ion is less stable. Now, in phenol, the anion formed is stabilized by delocalization of the negative charge over the benzene ring. So if you said this, or indicated this in a diagram, you would get 1 mark. And in alcohols, the anion formed is not stabilized by delocalization. In fact, the alkyl group pushes electrons onto the O to make it more negatively charged. So if you said it's not stabilized or it's made to be less stable, you would get a mark for that. And to get the 3rd mark, you have to say that carboxylic acids have more stable anions because the electrons can spread over the 2 oxygen atoms and the carbon. So there's a mark for that. And if you said that this delocalization is stronger in the acid than in phenol, there's a mark for that. And if you said phenol loses H plus more easily than alcohol, or there's more H plus in solution than with alcohols, and carboxylic acids loses H plus more easier than phenol, and there's more H plus in solution for carboxylic acids, you get another mark. So there's a maximum of 4 marks available here. So you don't have to get all the points, you just have to get any of these 4 points to get the maximum marks on offer. Now for question 3, you're asked to explain why methanoic acid is more acidic than ethanoic acid. And this is a 2-mark question. Now this comes down to the stability of the anion. The anion that forms for methanoic acid is more stable than the anion that forms for ethanoic acid. And this is because the alkyl group pushes electrons onto the oxygen. And this makes the anion less stable, so there's less H plus in solution. So 1 mark if you said the ethanoate ion is less stable than the methanoate ion, and if you explain why, you get the 2nd mark. So that concludes this video lesson. So after watching this video, you should be able to describe the intermolecular forces present in carboxylic acids and be able to explain how these are linked to physical properties such as boiling points. You should also understand why carboxylic acids are classed as weak acids and how their acidity is affected by increasing the hydrocarbon chain length in the molecule. And finally, you should be able to explain the order of relative acidity of carboxylic acids compared to phenols, alcohols and water, and how this can be demonstrated. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.